Hi and welcome to my channel. I'm going to be doing a COMSOL tutorial today on droplet evaporation on a solid substrate. For macroscopic droplet in quiescent atmospheric conditions, the rate limiting step for evaporation is the diffusion of vapor in air. The vapor concentration at the droplet interface is assumed to be in local equilibrium, contained by the saturation vapor density, which depends on the surface temperature. So the physics interfaces we're going to use today are two-phase laminar flow with a moving mesh to track the water-air interface. So this is new. This is something a little different that I haven't done before, and my last tutorial we used the level set method. Moving mesh is another method you can use instead of level set for moving boundaries like in evaporating water droplet, or for deformities that are continuous with the process. Fluid-fluid interface that incorporates evaporative mass flux. Transport of diluted species module to account for the water vapor diffusion and convection through air, which predicts the evaporation rate. And also the heat transfer in solids and fluids. For non-isothermal flow, temperature-dependent saturation vapor density at the droplet interface, latent heat of evaporation, and substrate heating effects. And then on the outside of the infinite layer, the curved edge on the very outside, you have C infinity, or the bulk concentration basically. And we're using an axisymmetric model. And then the heat transfer in solids and fluids, we'll use an adiabatic condition where T solid, temperature of the solid, equals the infinite temperature or the bulk temperature of the air plus the change in temperature. Other boundary conditions, the saturation vapor pressure is given by the Antoine equation, and the saturation vapor density is given by the ideal gas law. So we've got log 10 of P sat equals A minus B over C plus T, the Antoine equation. And C saturation equals the saturation pressure over RTM. This is just the ideal gas law, PV equals nRT, where of course the concentration is just N over V. Moles over a volume gives you concentration. If you do a units analysis, dimensional analysis, you've got something like moles per meter cubed. Equals, so N over V equals P over RT. The evaporative mass flux at the interface is given by the diffusion of water vapor. J equals molecular weight times N, which is a surface normal vector, times the negative of the diffusion constant of vapor in the air times del concentration, or the concentration gradient. And that gives you the total evaporative mass flux between the air and liquid. The Lagrange multiplier is used for an accurate boundary flux, and a conditional statement is used to regularize singularity at R equals 0. Okay, so we'll see that once we get there, but singularities often happen in COMSOL, which is basically just a difficulty in computation because you've got one dimension too small. So for instance, if you used 1 point instead of a line, if you use a one-dimensional boundary instead of a two-dimensional for 3D computation, it can create a singularity. Or in this case, we're doing an axisymmetric model. So apparently we have to use the Lagrange multiplier to create an accurate boundary flux, along with a conditional statement and if then statement. Okay, and then the latent heat of evaporation, L, is incorporated at a boundary heat source, negative JL, in units of watts per meter squared. So our total evaporative mass flux times the latent heat of evaporation. And that will be one boundary heat source. All right, in order to implement it, here's our fluid-fluid interface with evaporation. Here's all of our physics I already mentioned, along with a global ODE mathematics interface. So the moving mesh with fluid-fluid interface is used to track the shrinking water droplet. Mass transport at the fluid-fluid interface is coupled to species transport. Infinite element domain for specifying boundary conditions very far away. So we've got bulk air very far from the boundary, the air close to the evaporation. Navier slip condition for the wall for moving contact line, which would be the water line. And, for the moving contact line here, and the boundary heat source to account for latent heat of evaporation. We're breaking bonds between water molecules, which requires energy, and it's becoming cooler. So it took some energy to evaporate, and that then reduces the temperature of the surrounding air phase. So that's where we're taking into account the latent heat of evaporation. Finally, non-isothermal flow coupling between heat transfer and fluid flow. Okay, so the results are going to look like this. The evaporation dynamics of a water droplet in air on a heated solid glass substrate can be predicted. So here we've got the color legend from 20 to 36 degrees Celsius in our water droplet evaporating and shrinking from 0 minutes to 8.5 minutes elapsed. All right, and then this is about verification of the isothermal case against the analytical results, so we can do that at the end. And the non-isothermal case shown in blue here against the isothermal case in green. But there is no tutorial accompanying it, so once again, I'm going to be using the completed model as a guide and doing it from scratch. All right, so the first thing we want to do is create a model wizard and use the 2D axisymmetric model. And then we'll select all of the physics and mathematics modules this time. So we're going to choose laminar flow under fluid flow. Single phase flow, laminar flow. Click add. And then I'm going to select transport of dilute species, which is the first item under chemical species transport. Heat transfer and solids and fluids, which will be under heat transfer in solids and fluids, the third one down. And finally, we'll go to the mathematics section at the very end and choose GE. So this will be under ODE and DAE interfaces, and then the first item is global ODEs and DAEs. And add. Ordinary differential equations and differential algebraic equations. Okay, so I think that's all we need. And then let's go to study. And we're gonna have two different time-dependent studies here, but to get started, we'll just do one time-dependent study. So the first thing we want to do is import the global parameters. So I'm going to load from file, and I already exported the droplet evaporation parameters from the completed file. So in this list, we've got the diffusion coefficient of water vapor and air, LH, the latent heat of vaporization, A, B, and C, which are all Antoine equation constants, RS, the specific gas constant, MW, the molecular weight of water, delta T, the substrate heating, RO, the initial drop radius, which we'll use in the geometry, H0, the substrate thickness, sigma, the surface tension, T iso, the isothermal case temperature, PSAT iso, which is the saturation vapor pressure for the isothermal case, ρsat iso, and ρw iso, which are the saturation vapor density and water density, respectively, for the isothermal case. And for this last one, it's red because we've got a function we haven't defined yet. Next, we need to do the geometry. So for geometry, we first want to build a circle. So the radius of the circle is going to be 20 times r0. Sector angle is 90 since we're only drawing a quarter of the circle. We'll keep the base center at the origin, and we're using polar coordinates since we're doing axisymmetric with the circle. There's our circle. It's 90 degrees because we've chosen to only draw 1/4 of the circle and rotate it about the axis of symmetry, or the y-axis. This will produce a hemisphere that we're interested in looking at the evaporation of a smaller droplet, which will be down here. Next, we're going to build a rectangle with width 5 times the drop radius and height h0 from our parameters. And it's also centered at the origin and polar coordinate. All right, now we're ready for the droplet semicircle or quarter circle, and this will have a radius of r0, the drop radius as we defined it, with sector angle 90, and it's going to be centered at the origin and transformed up by 0.00, or we can just say h0. Alright, so there's our droplet. And then one more boundary. Alright, so the first time around I actually made a third circle, but we're supposed to use layers here for the infinite element domain. So layer 1 has a thickness of r0, which is the radius of the water droplet. And as you can see, it's the same thickness of that external element. So the first layer inward from the outside of circle 1, and then layer 2 has the radius and sector angle defined. Layer 1 has the same sector angle, and radius thickness is from 20 times r0 to 19 times r0 in essence. From the COMSOL documentation, an infinite element domain node applies a real valued coordinate scaling to a layer of virtual domains surrounding the physical region of interest. When the dependent variables vary slowly with radial distance from the center of the physical domain, the finite elements can be stretched in the radial direction, such that boundary conditions on the outside of the infinite element layer are effectively applied at a very large distance from any region of interest. Okay, so we just add this under definitions, and under the component, infinite element domain, or you can right-click artificial domains under definitions. All right, and then you can choose your geometry as Cartesian, spherical, cylindrical, or otherwise, and then scaling, the default value is going to be 183 times d geometric characteristic, which leads to an infinite element domain that is very large compared to the geometry dimensions, and with a nearly singular 1/r stretching. We're going to go to component 1 and then definitions, and we're looking for infinite element domain. So over on the right towards the middle, and select only region 4. We've also got some variables to set up here, so I'm just going to export these from the completed file and save these as droplet evaporation variables, so I don't have to retype them all. but we've got the saturation pressure, so Antoine's equation here, and we've got the density, and we've got the saturation vapor density, the saturation vapor concentration, and the analytical solutions for the radius and volume respectively. So we can compare those in a 1D plot at the end. And finally, we've got a Boolean statement for the evaporative mass flux. So the statement is if radius is less than height over 1000, then it's this value, else it's this value. So if this condition is true, the expression is negative molecular weight times diffusion constant times quantity nr times CR plus NC times CZ. Otherwise, if the radius is greater than or equal to the height, 1,000th the height, then the evaporative molar flux is, evaporative mass flux is positive molecular weight, CLM times 1 over 2 pi r. Okay, so those are two flux values for the boundary condition. Definitions, local variables, and then we'll just import from file, load from file, droplet evaporation variables. There we go. Some of these are in gold because it doesn't recognize the function or operator yet, although it will shortly. And then we've got to add a step function next. From 0 to 1 at 0.05. There's our plot of the step function. Okay, once again under definitions, we're going to go this time to non-local couplings. Add the integration, the first option there, and you'll see intop1 is the operator name. For this one, we want to select the droplet domain, so domain 2. And what we want to calculate is the volume of the droplet with this integration operation. We'll call it volume integration, which means it is integration order 4. And we'll leave the default checkbox filled compute integral and revolved geometry for the spatial domain using R, phi, and Z coordinates. Okay, and then we want to add another integration operation. And this one's going to be for a point. So we want to change the geometric entity level to point. And we're going to go ahead and select this point where the droplet meets the heated glass surface. Why are we selecting this? Because this is where the geometry is deforming, or the geometry is moving as the water evaporates. So the Navier slip condition that we'll set once we get to it will move as this point changes. It's going to slowly shrink in until the droplet is gone. But we don't want to compute the integral and the revolved geometry. So we're going to uncheck that box. We'll just call it mesh displacement. Now we're ready to add our materials. So we've got two materials here, water and air. Technically glass as well, but we don't really care about that as part of the model. So let's go to add material and look for water liquid from the built-in materials in the material library. So here is water solid, water liquid. So I'm going to double click on that one to add it to the current selection, and then also we want air. And here is air, gas. Actually, we just want plain old air from built-in. Alright, so I've got both of those selected, and now we need to add the domain selections for each of the materials. So water, since it's the first one I selected, will be everything except that. So I'll just deselect everything except the water region, And then for air, we want the inner and outer circles, the infinite domain of air, and then the air in the near field. In the definitions tab at the top, let's click under moving mesh, and we want to add deforming domain. And then the only domains that are deforming are domains 2 and 3. Since this air is very far away, it's the infinite domain, and the glass, the solid surface, the solid surface that the air is on, the solid surface that the droplet is resting on is also not deforming. We'll keep the default values here. Now we want to add a prescribed normal displacement. So clicking on moving mesh and going under boundaries, prescribed normal mesh displacement, selecting only this boundary. Next, we will choose the fixed boundary, which is going to be the end of the glass, the bottom of this quadrant, and the inner boundary of the infinite domain. All right, now we're going to add under moving mesh, prescribed mesh displacement. And we'll choose the top, well, half of the top section of the glass, the part not under the droplet. And we're going to use this expression for the displacement. Mesh displacement is not defined yet. So if we go to our completed model, you can see this is our global ODE that's going to govern the moving mesh. So we're going to go down to ODE and type that in just so it's not showing as yellow. So mesh displacement, mesh underscore disp is our function name we're going to call by. And here you can enter in, you can see the global equations format, function of u or ut. In COMSOL, just writing a letter after the function means you're taking the first derivative with respect to that thing. In the same way, a subscript would look like this. Ut is the first derivative, utt is the second derivative with respect to time, or a function of time. And then there's spaces here for initial value of this function at time 0 and the first derivative with respect to time at time 0. So ours is going to be mesh displace first derivative with respect to time minus in top 2, which recall was the where we placed this Navier slip where the droplet meets the glass is where int op 2 is occurring. And as a function of SPF.Vn, single phase flow output Vn. So V is, remember our velocity, U, V, and W are the letters that correspond to each of the coordinates, and since we're using polar coordinates, our second coordinate would be phi. So in polar, it's R, phi, Z. So since V corresponds to the second coordinate, this would be the phi, basically the normal velocity, Vn. Well, let's see, basically what we're saying is we want to take the integral, we want to find the mesh displacement from where this, from the end of the droplet on the wall to where the end of the droplet is now, after some iota of evaporation has occurred. So this would be a function of single phase flow and the outward velocity, and initial values of both u0 and ut0 are both 0. So let's go back to the moving mesh prescribed mesh displacement. So finding the solution where the first derivative of this function with respect to time minus int op 2 of the normal velocity vector of the droplet is 0, that that function times Rg minus 5 times the water droplet, R0, over -4 times R0. So Rg, let's go back to our geometry, or component 1 rather. So if you click on component 1, you can see the spatial frame coordinates are phi z, material frame coordinates, geometry frame coordinates, and mesh frame coordinates. So all are phi z, and we just specify with lowercase, uppercase, or subscripts G or M, whether we're referring to spatial, material, geometry, or mesh coordinates. So normally we would just use the normal default value of the spatial coordinates. But in this case, we have a moving mesh. So we're going to use the geometry frame coordinate for R here in the prescribed mesh for Rg. And R0 is just a constant, the beginning droplet radius. So when the droplet is at the beginning, when the radius of the droplet is R0, which is only at the beginning times 0, this would be and now we want to add one more prescribed mesh displacement. Now this one's going to be at the interface where the water droplet comes into contact with the wall, the glass surface. And it's going to be the mesh displacement ODE times Rg over R0. Moving on to laminar flow. This is going to take place in the air and water boundaries. So domains 2 and 3. And the fluid properties are going to stay as default. Initial values will stay at default with a 0 velocity field, 0 pressure. Axial symmetry is already selected correctly, and wall 1 is just going to end up being just the top of the glass surface. So we'll need to add some other boundary conditions to remove these other remaining boundaries. So we'll right click on laminar flow and choose initial values and select the domain of the water droplet. So the pressure is going to start at 2 times sigma, which is the surface tension, over the radius of the droplet, and the velocity field is 0. And we're going to right click on laminar flow and add a fluid interface for a fluid interface. And we've got fluid here and fluid here, so here's our interface with an outward normal force. Instead of using the water air library coefficient for the surface tension coefficient, we're going to change this to user specified, user defined, and change it to our value of sigma. And then for the mass flux, we'll change this to the variable J, so it will reference the function we defined before. And for the contact angle, it stays the same as pi over 2 in radians. And that of course happens where we've got the moving boundary where the water droplet comes into contact with the wall as it evaporates. Next, we're going to add an open boundary at the interface between the near range air and the infinite element. So we'll go to open boundary and select boundary 12. And finally, we're going to add wall 2. So we'll add another wall since we've got wall 1 here. And we're going to select the side of the glass surface and the bottom of this domain. And it will have a no slip condition. Now we can go back to wall 1, which is the top of the glass surface, and change this to a Navier slip condition. And we'll keep the default value of 0.5 for FH, which is the factor of minimum element length. Transport of dilute species is only going to happen in the air surrounding the droplet. It won't happen in the infinite domain. It won't happen on the inside the water droplet or on the surface. So domain 3 is the only one applicable here. And transport properties 1, the first node underneath that physics. The only thing we're going to change here is under the diffusion section, change diffusion coefficient to D to reference our parameter. And then for axial symmetry, we'll keep that defaulted selection. No flux is going to happen. So we'll have to override no flux by adding more conditions to those. So we'll come back to that. Initial values, we're going to start out with a concentration of 0 in the air. And we've got no flux on the side or surrounding area of the glass. So it's just going to be this side wall and the bottom here. So that means we need different conditions here, here, and at the infinite domain. So we're going to right click on transport of diluted species and choose transport properties. And this is going to be in the, okay, so going back to the first node, the header node of transport of dilute species, we do need elements 3. We need to select domains 3 and 4. Even though there's not actually any transport of dilute species in this region, we still need to select this so that we can add a transport properties too. And then we're going to add our concentrations. So we'll have 2 concentrations. One here is going to be CSAT. By definition, the interface between the water phase and the air phase has got to be saturated because they're in equilibrium. And then right click on TDS again, add another concentration condition. And this time it's going to be at the interface of the near field. I'm calling it near field air. That's not really what it is, but just for lack of a better word. And the infinite domain. Infinite element domain. It starts at 0. Concentration 2 will be 0 at the outer bound of the infinite element domain, so boundary 13. Then when we go back to no flux, it should only be the top side of the top inside of the glass surface, the heated glass surface, and then the bottom of the air domain. Heat transfer in solids is going to happen everywhere except for the glass surface. There's no heat transfer during the evaporation with the heated glass. For fluid 1, we want to select the domains where the evaporation is happening. So domain 3, the water droplet, and domain 3, the air surrounding it. And we'll leave all the default values here. The only thing we're going to change under fluid 1 is under the thermodynamic section, change the fluid type from material to gas liquid. So the density will be from material, heat capacity at constant pressure, and ratio of specific heats. Initial values, I'm just going to leave the default of 293.15. Axial symmetry will stay the same. Thermal insulation, we only want the bottom part to be thermally insulated. If we go back to the slide, we've got adiabatic condition on the bottom of the domain, or the bottom of the model. So we'll have to add conditions to override the thermal insulation condition at the outer boundary of the infinite element domain and on top of the glass surface. First, let's add fluid 2 for the infinite domain, the infinite element domain. And we'll go to the top and click on fluid. There's already one fluid, so this becomes fluid 2. Adding element or domain 4 for the infinite element domain. The fluid type is going to be ideal gas. And we'll keep all the default values for this one. Then we're going to add a temperature condition. So from the PowerPoint, the tops and sides of the glass surface follow this equation. T solid equals the infinite temperature plus the change in temperature. So let's go ahead and select those boundaries. And then the temperature is going to be user defined as T naught, already defined as 293.15, plus delta T times step 1. Delta T is defined in the parameters as 15 Kelvin for the substrate heating, because remember this is a heated glass surface. And from our variables, or from our definitions, we've got step 1 turns on at 0.05. So why do we need this step here? Because we've got a delta T here, so if we didn't have a starting time 0 for the solver, it would run into singularities, I guess you would call it, where it can't solve. So you have to give it at least like a fraction of a second to have a base time to then calculate delta T for all times after that. So we just use a turn on function with smoothing, so it has a time 0 to start with. Then we want to add, going back to the PowerPoint, we need a boundary heat source as shown here on the outside of the water droplet. So let's right click on heat transfer in solids and fluids and choose, where is it? Here we go, under heat sources, boundary heat source. Choosing boundary 11, and the heat source, big Q, will be defined as negative J times LH, where J is our evaporative mass flux and LH is the latent heat of vaporization, 2264 kilojoules per kilogram. Then finally we'll add one more temperature condition. For the external boundary of the infinite element domain, just using the same value of 293.15 Kelvin. Okay, so now we've got to couple our physics. So let's go to the physics tab up on top, choose multi-physics couplings, and we're going to choose non-isothermal flow and also reacting flow diluted species. So the non-isothermal flow interface is going to couple fluid flow from the single phase flow and heat transfer from the heat transfer and fluids modules. And then the reacting flow diluted species is going to couple laminar flow and transport of dilute species. So we have a mass conservative coupling of these solutions as mass flows from this domain into this one and heat along with it. These need to be coupled because transport of dilute species is what is allowing us to model evaporation, the departure of mass from one domain into another. And as the water is evaporating, it's changing the temperature gradient in both domains. Moving on to the mesh. So first we're going to change this to extra fine. Alright, to start with, let's go to the mesh tab at the front, choose mapped, and then distribution. Mapped 1, we're going to change remaining to domain and select domain 4. Then for the distribution, we'll just have the boundaries on the end selected, boundary 6 and 10 with 5 elements. For domains 2 and 3, we're going to use a free triangular. And we don't want to use remaining, so let's change this to domain. Select domains 2 and 3 with the maximum element size R0, the initial radius of the droplet, over 100, and maximum element growth rate of 1.01. And build all. There you go, you can see rectangular elements by 5 on the outside of the infinite element domain, and then and a tighter free triangular mesh around the water droplet, and no mesh inside the glass surface because we aren't modeling that. Okay, moving on to study 1. We're just gonna label study 1 isothermal case. And for the time-dependent study, let's clear heat transfer in solids and fluids and non-isothermal flow. So we're only solving for laminar flow, transport of dilute species with the global ODEs and moving mesh. We're removing heat transfer, which means we also remove the non-isothermal coupling. And then let's model through 16 seconds in half-second increments. And then we'll add a second study. So let's go to the top under study, add study, time dependent. This one we will solve for all physics interfaces and multiphysics couplings, and this one will only go through 8.5 seconds and 0.5 second increments. So these are minutes. And one thing I need to change is the units. So both of these should be in minutes. Okay. All right, there we go. So let's hit compute. Okay, one more thing we have to add. So under isothermal, for the isothermal case, we're going to go to time-dependent study extensions at the bottom and add an auxiliary sweep. So let's add a row in the table here, and from the drop-down menu, select delta T for substrate heating. And the parameter value list we just keep at 0. Okay, and there's one crucial, very crucial checkbox we gotta change here. Under transport of dilute species, concentration 1, the water-air interface, you have to expand constraint settings and click the checkbox by use weak constraints. That's what's going to activate or permit the use of a variable for the Lagrange multiplier for an accurate boundary flux. So we have to use the weak constraints for that interface to accurately model the evaporative mass flux over that boundary. Okay, one more thing I found a difference between these is fluid 2, the infinite element domain. Under model input, I had to click the make all model inputs editable because this is by default grayed out, so you can't make changes. But it looks like we have to make the model input for temperature use the HT model. Okay, another thing on the global ODEs and ADEs, we've got to add custom units here. So instead of dimensionless, we're going to define the custom unit as meters and the source term quantity as meters per second. Because this is a function of, expand that a little, into op2 SPF.vn, so single phase flow. V is a velocity component in the phi direction in meters per second, so that's our source term quantity. All right, another difference is our compressibility. We've got to change the laminar flow compressibility to weakly compressible flow. Okay, one last thing it looks like they did. Right click on time dependent solver and choose fully coupled. And then we're going to change the linear solver drop down menu to select direct concentrations instead of direct fluid flow. I also disabled segregated just by right clicking and hitting disabled. And some of the other things in here I was not able to disable. So let's see if this works.